thank you, President McCormick, and I'd like to say how honored I am by your and my colleagues' choice to appoint me to this lecture. And I hope we can all have some fun this evening learning something about astronomy. As you know, most branches of physics these days are extraordinarily complex, and usually progress is made by large teams of scientists working together rather than individuals. This has certainly been the case in my own research. And in this kind of model of doing science, there's basically two ways to succeed. You can either be very smart, or you can have very smart people working with you. And in my case, I've chiefly chosen path B. And so I want to acknowledge, first of all, the long list of undergraduate students, graduate students, postdoctoral fellows, and faculty colleagues of mine that have really made it possible for me to understand the small about the universe that we do understand. There are many such people, but I cannot but help singling out two people who have collectively worked with me for 30 years and to whom I owe a huge debt, and that is Professor Scott Anderson and Dr. Eric Deutsch, and I really do appreciate their collaboration. Well, let's get started by musing on something that's fun to think about, which is the relationship between art and science. In both fields, you can work very hard to solve a problem, succeed at solving the problem, only to discover a more detailed and intricate problem within. And that is the case in the problem that we're going to talk about tonight, which is what is the universe made of and how did it get that way? This is hardly a new problem. If we look at sort of the exterior of the problem, it's certainly true that at least since the ancient Greeks, people have been pondering whether there is a continuity of matter or whether matter comes in discrete chunks. That is, if you take a grapefruit and chop it in half, you have 2 pieces. If you chop it in half again, you have 4 pieces. If you chop it in half again, you have 8 pieces, and so on. Can you do that forever, or will you eventually reach some minimum possible unit? Well, 2 millennia ago, this was argued by the Greeks, by people such as Democritus and even Plato. It turned out they both reached the same conclusion, that there was a minimum indivisible size, and in the remarkable spirit of even 21st century science, they fought with each other over who reached the conclusion first. In the millennium just ended, these thoughts are often attributed to an English natural philosopher by the name of John Dalton. But in fact, the concept that the universe is made of atoms is something that has really evolved over millennia of human thinking. And so I would argue that this first doll is now sort of parsed. Yes, there is a minimum divisible unit, and we call that unit the atom. We actually know quite a bit about atoms. That is, experimentally, we have verified many things about their properties, and I'm going to tell you just a few things in a moment or two. And so actually the second doll in the sequence is fairly well filled out. We know what's inside atoms and how much they weigh and how much electrical charge they carry and things like that. But what I want to talk about today is perhaps an even more ambitious topic, the third doll down, which is how were atoms originally manufactured? Okay, there is a minimum size piece of matter. It's called the atom. We understand some things about it. But how were the atoms made? It's kind of the frustrating question that a 2-year-old keeps asking you. And sometimes these most basic questions are the very hardest. It turns out that our generation is the very first generation to know the answer to this question. When my father and mother went to school, no matter how smart they were, no matter how hard they studied, no matter how smart their teachers were, if they asked the question, how were the atoms originally made? The answer always was, nobody knows. Well, now we know, and in that sense, we're in a special generation. We are really the first people who can absorb this material and understand this question, and in fact, that's the goal of our talk this evening. So we'll start out talking a little bit about the structure of the atom. Lock the doors. Okay. The atom is actually remarkably simple. It's a tribute to Mother Nature that she was elegant in deciding how to manufacture the atom. As all of you know, it consists of a central piece, which we call the nucleus, and some bits of electrical charge circling around the outside of the nucleus, sort of like a little solar system, and we call those electrons. The electrons don't play much role in what I'm going to discuss tonight, so most of the time I will omit them. There are 2 basic particles that you can insert into the nucleus of an atom. One is called the proton, and the other is absolutely identical to the proton, however, it lacks the electrical charge that the proton carries. So I've made my proton sort of colorful to show you that it has something extra, has a little bit of electricity. The neutron is sort of the stripped-down version of the same thing. It's exactly the same as the proton, but it lacks the electricity. And that's essentially it. Those two particles go together to build every atom in the universe. Now, I'd like to tell you that there's only one way you can put them together. That would be extremely elegant. It turns out not to quite be true. Nature has chosen about 120 different building blocks. Now, that might seem like a large number, but I would actually argue that it's a small number. I mean, our galaxy of stars, the Milky Way, contains 200 billion stars. There are at least 10 billion such galaxies visible to the largest telescopes. That's an opportunity for an awful lot of diversity in the universe. But what actually happens is that every piece of matter in the universe follows this pattern of having only protons and neutrons in the center of the atom, in the nucleus, and a limited number of ways to construct them. So let's talk about those different ways. Well, the simplest possible construct you could imagine is an atom that consists of just one proton. You certainly can't be any simpler than that. And indeed, it turns out that nature decided to make 90% of all atoms in the universe of that simplest possible thing. And just for shorthand, to make it easier for a physicist to talk to another physicist or for a teacher to talk to the class, instead of saying, I'm talking about that simplest possible atom that has only one proton in the nucleus and no neutrons, we give it a name, and we call it hydrogen. So we can say, I'm talking about the hydrogen atom, and you instantly know that's just an abbreviation for one proton, nothing else. If you think about the next most possible complicated nucleus, it turns out that's one that, of course, contains two protons, and in this case it has a little extra trim, namely two neutrons, and we call that the helium nucleus. Nature turns out to have made 9% of all the atoms in our universe of helium. So actually, we've already discussed 99% of the matter in the universe. 90% hydrogen, 9% helium. Thank you very much. No. In fact, it turns out that the 1% of remaining matter is the matter that is really most important to you and me. You're probably aware that your body doesn't have much hydrogen in it. Your body doesn't have much helium in it. The Earth, in fact, doesn't have much hydrogen and helium either. It's also possible to have kind of options if you pay a little more money on these nuclei. So you can sort of get chrome alloy wheels by adding extra neutrons. So for example, if you add, I neglected to say that the next most complicated nucleus upwards is lithium. That's 3 such protons and so on. If you add an additional neutron to the hydrogen atom, you almost have hydrogen, because it's hydrogen with an extra neutron, and we call that deuterium, or we call the nucleus the deuteron to be exact. And actually, deuterium is very placid stuff. About 1 out of every 4,000 hydrogen atoms on Earth is deuterium anyway. So you drink it with water every time, and you really never know the difference. You can also subtract neutrons if you want some more variety. So for example, if you take one of the neutrons away from the helium nucleus, so you have 2 protons and only 1 neutron rather than 2, we call that helium-3. And you may remember from your high school chemistry that these things are called isotopes. And I tell you this footnote just because these 2 particular isotopes, deuterium and helium, play a role in the rest of what we want to talk about tonight. Now, you can continue to build nuclei of ever greater complexity just by adding more protons and more neutrons, but it's not infinitely complex. And as I mentioned before, in fact, there are only about 120 permutations or so that are found in the universe. And we call these 120 permutations the periodic table of the chemical elements. So all this is the full Sears Roebuck catalog of every possible nuclei that nature has decided to make. And they all have names. You see, here's the hydrogen and helium and lithium, the 3 simplest things. And then we go up through beryllium, boron, carbon, nitrogen, oxygen, and so on. And actually, once you get beyond about the 2nd or 3rd row, those nuclei turn out to be incredibly rare in the universe. After all, everything besides hydrogen and helium is just 1% already. And so the bottom rows of this table play little role in what I want to say. And anyway, nobody can pronounce or spell them anyway. So the real issue here now is, okay, we understand that this is the structure of matter. We might choose to marvel a little bit, by the way, that we have observational evidence that this precise same set of rules is followed everywhere in the universe. I will not go into that today, but I want to stress to you that this is not a philosophical musing. We can prove this through observation. So the faculty lecture taking place in the Andromeda Nebula tonight, they are looking at this same chart of chemical elements and marveling that there are only 120 possible ways to put these things together. The question that we want to confront now is, well, who did put them together? How were they put together? When were they put together? Did it happen only once? Is it an ongoing process? It's just the kind of infuriating thing your child asks you as he or she is educated. You give one answer and they say, but why? And then you give another answer and you say, but why? And you give another answer and you say, go wash up for dinner, right? There's a wonderful scientific cartoonist who I recommend to you by the name of Sidney Harris, who really understands the nerd in scientists very well and publishes cartoons about sort of fundamental issues in the physical science. And he summed up this issue, this difficulty of telling where particles came from, very nicely in this cartoon. If only you just had a microscope and you could peer and it said, made in Hong Kong, we could all go home. But in fact, every hydrogen nucleus looks pretty much the same. It's a proton, they all weigh exactly the same amount, they all have exactly the same electrical charge. They don't tell you where they came from. So sometimes these easiest problems are, in fact, the most difficult ones to answer. Well, I'll give you the bottom line of this evening's talk right now. All of these 120 possible nuclei come from the stars. This is a lecture in astronomy. I'm a professor of astronomy here at the University of Washington, and something that many, many people do not realize is that all of those 120 nuclei that build everything in the universe, not just stars and galaxies and gas, but trees and giraffes and people, they all come from the stars. And our goal this evening is to explain how. Now, many of you may know that on a large scale, the basic unit of structure in astronomy is this assemblage of stars that we call a galaxy. It's a collection of some 200 billion separate stars that are trapped together by their mutual gravity and cannot escape. And in fact, there are so many of them so close together that they overexpose the photograph. If you could step out of our own Milky Way galaxy, travel a few million light years, turn around, look back and take a photo, this is what we believe our home galaxy, the Milky Way, would look like. In fact, this is a picture of the nearest neighboring large galaxy to our own galaxy called the Andromeda Nebula. And the fascinating thing about the structure of the universe is, just like the nested Russian dolls, these galaxies go on and on and on beyond the limit of our ability to observe them. So if you take a more sensitive photograph, you open the shutter for longer and expose for longer so you can accumulate more light, you see more galaxies. And every one of these things is 200 billion stars far outside the Milky Way. That's 200 billion stars, that's 200 billion stars, that's 200 billion stars, that's 200 billion stars. If you expose deeper to look to yet fainter things, you see more galaxies, farther away, fainter, and so on. There is no indication that we have reached the limit. Many of the results I'm going to tell you tonight are due to this splendid instrument, the Hubble Space Telescope, which orbits some 350 miles above our head around the Earth once every 90 minutes. I've been privileged to be associated with this project virtually since its inception 25 years ago. And what I'm going to show you now is an attempt by Hubble to find the most distant possible galaxies. And I will tell you right now that it failed. That is, no matter how faint you expose, you never seem to reach the limit. When you want to take a more sensitive picture with your camera, you take a time exposure. You open the shutter and you leave it open for a while so it can accumulate more light. If you want to take an even fainter picture, you leave it open a long time. Hubble was used about 3 years ago to take the most sensitive astronomical image ever made. The telescope was pointed at a tiny patch of unremarkable sky in the constellation near the Big Dipper. The shutter was opened, and it was left open for 10 consecutive days, 240 hours of light gathering capability. And now remember, we're looking at just a teeny piece of sky, about 1,000th of the size of the full moon, and I'm going to show you the results of that Hubble image in the next slide, and I'd like you to sigh, please. That wasn't very good. We're going to have to work on that. Okay. In this faintest possible image ever seen by humankind, everything is a galaxy. That's 200 billion stars, that's 200 billion stars, that's 200 billion stars, that's 200 billion stars, that's 200 billion stars. And even the teeny little fuzzballs that you probably can't see, but I can, are all galaxies of 200 billion stars. It's a fairly natural question to ask, is there motion in this universe of galaxies? Are they all stationary, or are they moving in some pattern, or are they moving in some chaotic fashion? Indeed, the force of gravity is only an attractive force. Every atom in every star of all 200 billion stars, in every galaxy of all 10 billion visible galaxies, is attracting every other atom in every star and every galaxy throughout the universe. So there is this force that is trying to make the universe be in motion. And if you think about it philosophically, you then might conclude, well, from that argument, I might not be able to tell whether the universe is going this way or going that way, but I certainly wouldn't expect the universe to be stationary. Because if the universe were absolutely stationary, that would mean that the gravitational attraction of every atom and every star and every galaxy for every other galaxy exactly balanced out. And the whole universe would be like a house of cards set on edge, and you'd be afraid to walk a few steps to the side, because then your gravitational attraction on all these things would change the structure of the whole universe, and it could collapse, and it would be your fault. So, intuitively, you probably would realize that the universe is probably in motion. By the way, this was a difficult step for Einstein to swallow. He didn't like that idea. Well, there's actually a person who helped observationally prove to us that this universe of galaxies is in motion. And you probably know about this fellow, Edwin Hubble. Born in 1889, died in 1953. He was an observational astronomer, that is, he used telescopes to gather data. He was interested in galaxies and the motion of the universe. And he, plus a number of closely working colleagues, used these observations to prove that not only are the galaxies in the universe in motion, but they are moving apart from each other systematically. Everything is moving away from everything else. I once had an Astronomy 101 student answer the question, what did Hubble prove? With the answer, all galaxies are moving away from the Milky Way. Can you blame them? It is true, in fact, that all galaxies are moving away from all other galaxies. The universe is expanding. So the next time you sit down on a plane and someone says to you, what'd you do last night? And you say, oh, I went to a lecture on astronomy. And they say, oh, do they still believe in the theory of the expanding universe? You can already correct them and say, no, that's not a theory. That's a fact. That's observed. That's like saying the theory of the apple falling off the tree. That's not a theory, it happens. The universe is expanding, it is getting larger. Well, the disquieting thing about accepting that is that if every moment, if galaxies move further and further apart, then of course you can mentally play the movie backwards. And you can realize, well, yesterday's universe was a little smaller. And a week before that, the universe was a little smaller still. And a billion years before that, the universe was smaller still. And of course, you arrive at the conclusion that the universe must have a finite age, because you cannot play the movie backwards any farther than when everything in the universe is merged upon itself. And so maybe you might intuitively accept, okay, the galaxies are in motion, but then you have to accept this very remarkable conclusion: the age of the universe, at least in its current incarnation, is finite. So we actually can almost talk about playing the movie backwards. Here we are today. To know how fast the movie is playing backwards, we simply need to know how fast the universe is expanding today. Then we know how fast to play the movie backwards. Hubble and subsequent generations of observational astronomers have measured this speed of the current expansion. So we know how fast to play the movie backwards. And the answer is 15 billion years ago, the universe, at least in its current stage, must have begun. You run out of movie at that point. Everything is squished into the same small volume. And so today means 15 billion years ago, and you can picture a smaller universe, a smaller universe, a smaller universe, and so on. And of course, because the event that began this expansion must have been very violent to set every atom in the universe in this outward expansion, the name that we give to this event is traditionally the Big Bang. Now, many of you may say, 15 billion years, how can I possibly even bother with that? I mean, that's such a ridiculously long time. What does it possibly mean to me? Well, I want to tell you that the Earth and Sun are 4.5 billion years old. If you lean down and scoop up some rock, you're holding some atoms that are 5 billion years old. which is a third of the age of the entire universe. So in fact, although some might say the universe is incredibly old, I might actually say the universe is rather young, because you can pick up common rocks that are a third of the current age of the universe. Now, there are both astonishingly large numbers and astonishingly small numbers involved in astronomy, and we're going to talk about some of both. As you play the movie backwards, the laws of physics, as we understand them, allow you to understand the physical conditions in the universe at that time. That is, we know how many atoms are in each galaxy today. If we play the movie backwards a week, we can calculate that everything was a little closer together. The universe was more dense. There were the same number of atoms in a slightly smaller volume. And as we play the movie backwards and backwards and backwards, we discover that the individual galaxies must have merged together. There wasn't room for more than one. The individual stars must have merged together. The individual gas in the stars must have been all together. The individual atoms in the gas must have been all together, and so on. Now, you might say, well, there must be some limit. There must be some point in our knowledge where we must say, stop, I can't tell you what the universe looked like anymore. All the material is so smashed together in such a small volume that I run out of laws of physics. I'm not infinitely smart. And the fact is that there is such a point, and that point is 10 to the minus 43 seconds after the Big Bang. Now, physicists and mathematicians have this strange nomenclature for small numbers. So let me tell you what 10 to the minus 43 seconds means. Okay? So we can follow the universe backwards until this briefest instant, slightly after the Big Bang, and tell you what was going on. We can tell you the temperature of the universe, we can tell you the density of the universe, we can tell you the chemical state of the universe, and we finally run out of oomph, this briefest flash. Well, okay, so if you don't mind not hearing about the first 10 to the minus 43 seconds, let me tell you about the universe. Now again, you might say, these numbers are impossibly large and small. How can you possibly describe the Big Bang to me that way? And I have to tell you that it's not easy. You're not the only one whose brain sort of spins at the large and small numbers involved in the Big Bang. So I turn again to Sidney Harris, the cartoonist. And I really love this because it's true, right? Here you have the professional rocket scientists talking to each other about the Big Bang, and the caption is trying to describe the size of the Big Bang, right? And they're sort of at a loss too, you know, it's real big, right? So yeah, it's real big, and some of it is real small, but we know now how to play the movie backwards. Let's look now at the first few seconds and minutes after the Big Bang goes off. Well, at that point, the instant after the Big Bang, we have an impossibly thick soup of fundamental particles. In fact, the universe is so dense and so hot that the protons and neutrons, which are later going to be our basic building blocks of atoms, cannot stand alone. Because as soon as one is built up from more exotic things like quarks and subnuclear particles, it instantly smashes into something else and is destroyed again. So the early moments of the universe are the original nature's Cuisinart. Everything is jumbled up. Every time you make something, it gets mixed back into this raw soup where almost nothing is recognizable. But remember, now we're playing the movie forwards. So the universe is getting larger, same number of particles are filling a larger volume, larger and larger and larger, so the universe is getting more and more and more dilute in any little given one area. The temperature starts to fall down from the impossibly high temperatures of the original Big Bang, and eventually collisions of fundamental particles make protons, those original building blocks of atoms, and the protons can survive. The universe gets big enough, so the collisions get rare enough that the average proton can go on its merry way and live its life for the rest of the 15 billion years of the universe. In the first few minutes after the Big Bang, however, another fascinating process occurs with those first protons that we make. So here's an original hydrogen atom. Now, of course, we don't even need Sidney Harris's made in Hong Kong. We know that the label says made in the Big Bang. It is possible in the first few minutes for hydrogen and the first neutrons that form, because this is still a highly dense environment with particles moving around like crazy, lots of collisions, to collide with each other and stick and meld. And hydrogen and a neutron together can form this isotope of hydrogen that we saw at the very beginning, which we call deuterium. The deuterium is also in this Cuisinart that's constantly melding it around at these very high temperatures. Two deuterium atoms can stick together and meld. And if you step back and you look at the result of two deuteriums merging, sort of like a conglomerate, you now have two protons and two neutrons, and you realize, hey, that's what we call helium. So in fact, helium is manufactured in the first 3 or 4 minutes of the Big Bang by taking advantage of collisions between hydrogen, protons, and neutrons to make deuterium and then make helium. One further nucleus is made in this very earliest stage. It's possible for helium nuclei to combine and make just trace amounts of that next most complicated nucleus in the periodic table, lithium. Interestingly enough, you can ask the nuclear physicist who knows nothing about astronomy, who's never been outside to look up, in Seattle even if he has been outside to look up, who's seen nothing about the stars, you can ask, hey, I know the physical conditions in the first 3 minutes of the universe. It was this hot, it was this dense. After you play this movie for 3 minutes, what would you expect? And the theorist can calculate a little bit, nothing to do with astronomical observations, and can come up with a result. It says here that 90% of all the protons made in the first 3 minutes should escape unscathed. About 9% of the protons in the first 3 minutes should be converted into helium nuclei, and about 1/10,000,000th of the nucleons in the first 3 minutes should be converted into lithium nuclei. And that's my prediction just from knowing about nuclear physics. Well, as I told you at the beginning of the evening, the observed ratio of these elements that the astronomer derives in the universe is exactly that. We actually observe 90% of today's universe is hydrogen, 9% is helium, 1% is everything else. And we even observe that the number of lithium nuclei in today's universe is about 1/10,000,000th of all the nuclei, in precise agreement with what the theoretical prediction is about cooking in the first 3 minutes. So if you wonder, is this all a myth? Did the Big Bang really happen? If you turn to the nuclear physicist and say, take me a bunch of protons and turn them into 90% hydrogen, 9% helium, 1% everything else, and 1/10,000,000th lithium, the theoretical computation will be something that looks like just the Big Bang. So the fact that we actually observe this around us today is strong confirmation that it really happened. However, if you're a skeptic, this is, after all, a pretty amazing story. It turns out that there are other diagnostics available to us as well. Well, let's step back now and ask what we've accomplished. There are 120 possible combinations of nuclei in the periodic table. I have now told you how the first 3 of them are made. I have told you how the simplest one is made, hydrogen. It freezes out of the primordial Big Bang. I've told you how the next 2 are made, helium and lithium. They're made by collisions in that first 3 minutes. Now you might say, gee, is that the rest of the story too? Are we going to build up all the other 120 nuclei that way? The answer is unfortunately no, because as the universe continues to expand, as you continue to play the movie forwards, it very rapidly gets too dilute and too cool to do any more of these collisions. So you can only make hydrogen, helium, and lithium this way. But hey, that's pretty good. I mean, you might say, what do I care about hydrogen, helium, and lithium? Well, I mean, every time you take a glass of water, H2O, right? 2 hydrogen atoms, 1 oxygen atom in this water. That's pretty good. Those protons come from the Big Bang. They're 15 billion years old, and you're just drinking them. So hydrogen is all around us. How about helium? Well, you might think, that's something very exotic. We haven't seen that since the Hindenburg or something. I mean, helium is not that exotic. There actually turn out to be other sources of helium manufactured in the universe, but not many. Most of the helium in the universe is made in the Big Bang. Well, lithium, I mean, surely that's too exotic to care about. The antidepressants that we all take, made in the Big Bang. Now, I mentioned that there were other sort of diagnostics that this really happened, and I want to just very briefly tell you about 1 or 2 of them. You notice that as the universe starts to get larger and a little cooler and a little more dilute and so on, that there's this era around a few 100,000 years where there's this very nice blotchy pattern on my pie here. It turns out that at that point, you can theoretically calculate that the universe starts to make light. It's essentially static left over from the violence of the Big Bang. And the light that is manufactured then percolates out through the entire universe in the form of microwave radiation. the same thing that heats up your donut in the oven. And those microwaves permeate every little piece of the universe still today. How do we know that? Here are two physicists named Penzias and Wilson, who worked in the 1960s at the research arm of the Bell Telephone Company. That was in the days, of course, when there only was one phone company. You could understand your bill and all that. And they had a research arm called the Bell Telephone Laboratories, located in Holmdel, New Jersey. They built this antenna to communicate with telecommunications satellites in Earth orbit, and they serendipitously discovered this static left over from the Big Bang. It surrounds us. It's in every little corner of the universe. It is of exactly the properties that are appropriate to have been made in the Big Bang. We can see the leftover sizzle all around us today. There's no other way to explain this radiation. Okay, well, how did the universe then evolve after the Big Bang? We've made hydrogen, helium, and lithium. That stuff became a gas, which cooled and formed into galaxies of stars, and then gradually collapsed into individual stars that we see around us today. I want to let you in on another dirty little secret of astronomy, which is that most professional astronomers don't know anything about the constellations. I know the Big Dipper and Orion, that's it. So here's one of my two constellations. That's Orion, right? You know, you can see his arms and his leg and the belt and the sword and all that. But you can also see that actually stars are of different colors. You can see a very blue star here and a very red star here. And that's because stars gradually age and evolve. How do they do this and why do they do this? It's actually a very interesting story. You know, stars are not a solid body. If you had a long enough arm and a good glove, you could put your hand right through the sun and it would come out the other side. It's just a loose bag of gas. And so this leads one to wonder, well, then how do stars hold themselves up? I mean, our sun is actually 700,000 kilometers across, but it's not a solid body. There are no girders. Why doesn't it just collapse under the force of gravity? Indeed, gravity is trying to collapse all stars, and the stars have a clever way of fighting back. Namely, the centers get very hot from this tendency for gravitational collapse, and the individual nuclei in the centers merge together to form heavier, more complex nuclei, just the way we saw hydrogen merge to become helium in the early stages of the Big Bang. And therein release a little excess energy. That energy percolates out through the star, fighting against gravitational collapse, holding the star up. And so, in fact, not only does the Big Bang cook more complex nuclei in the first 3 minutes, stars throughout their entire existence cook more complex nuclei in their centers while they are trying to fight back against gravity. As stars evolve, they first convert hydrogen into helium, but when they convert almost all the hydrogen to helium that's available to them in their cores, they then go through a very complex set of diseases and manipulations, and many of them expand up and become cool in their outer layers, but very hot in the center. We call such sort of middle-aged stars red giants, and you see Betelgeuse here as a classic example of a red giant. And what's going on in the center of that star is building up of complex nuclei. Here, a red giant in its very center, where it's extremely hot, can take two helium nuclei, collide them together, and make something bigger and more complex, namely beryllium. Other stars can then take beryllium nuclei, collide them with another helium nucleus, and make something more complex, namely carbon. So the centers of stars can take the hydrogen and helium that they were gifted with in the Big Bang and cook more complex nuclei. So our goal here, of course, was to explain how do we make everything in the periodic table. Well, we've seen that the hydrogen, helium, and lithium come from the Big Bang. We now have a process that can make a considerably large number of other of the chemical elements. In fact, you can make boron, carbon, nitrogen, oxygen, sodium, and so on, all the way up to iron. It turns out that no matter how hard the star tries, nature has a little footnote at the iron nucleus, and if you try and squeeze two iron nuclei together, they are so clever that they resist, and the star gives up trying. It's just not energetically profitable to squeeze iron together. But look at what you can make in this cooking process in the center of red giants. You can make nuclei that are incredibly important to us. For example, take a deep breath. Right? What are you breathing? 80% nitrogen, 20% oxygen. Where were they made? in the center of a red giant star. What's in your skin? Mostly carbon. Where was it made? In the center of a red giant star. Now you might say, hey, I'm not born yesterday. I'm not in the center of a red giant star. How did those atoms get to me? I mean, even if I believe you, how did that nitrogen and oxygen nucleus get into the air I'm breathing? How did that carbon nucleus get into my skin if it started out in the center of a star? It turns out that evolved stars offer free home delivery. In the very latest stages of stellar evolution, here's the star in the middle that used to be a red giant, the outer layers of the star start to drift off into the gas in between the stars, which we call the interstellar medium. For a change, that sort of makes sense. The gas between the stars is the interstellar medium. And that gas is enriched with these heavy elements, these complex nuclei like carbon, nitrogen, oxygen, and so on, that have been cooked there. The names of these structures, by the way, are an interesting joke in the history of astronomy. These are called planetary nebulae because they have nothing to do with planets and nothing to do with nebulae. Go figure. But they're really pretty to look at. And I have some shots from Hubble Space Telescope to show you some of these structures. Unfortunately, none of them are really visible with the naked eye. My favorite one is perhaps this one. I mean, it's just awesome. In a totally dark room, this actually sort of gives you goosebumps. It's, you know, because it's this single eye sort of staring at you, right? So the way that those complex nuclei, after being cooked in the center of red giant stars, get out into the rest of the galaxy is they are freely delivered out there. Now, of course, we have thus far found a way only to manufacture elements up through iron. Red giants are just not capable of cooking much more than that. How do we get the rest? Well, it turns out a very, very small fraction of stars are so massive that they just can't beat gravity. They desperately push nuclei together to make other nuclei. Some radiation emerges, trying to fight back against gravitational collapse. But they are so heavy that they are defeated by themselves. And these very most massive stars try and try and try, but just can't do the job. The most extremely massive stars burn this nuclear fuel from one nucleus to a more complex one to a more complex one faster and faster and faster because they are so heavy that they are incredibly hot in the center, and it's sort of like pouring gasoline onto a fire. Each time you get to a new nucleus, it burns furiously faster to get to the next one. And so in these very most massive stars, you in fact have the situation where some of these stages of burning, carbon going to neon, neon going to oxygen, oxygen going to silicon, just take a few years or even a few days before the process is totally exhausted again. And eventually, these very most massive stars lose the battle against gravity. They can't burn things fast enough to hold themselves up, and the star collapses entirely upon itself in a cataclysmic explosion, which we call a supernova. These are very rare events. They happen roughly once per 100 years in a given galaxy of 200 billion stars. The last nearby one in our neighborhood occurred not in our own galaxy, but in a nearby galaxy called the Large Magellanic Cloud. It happened in February of 1987. And you see here a before and after picture of that portion of that galaxy. And hey, even if nature hadn't put that little arrow in the sky, you would have obviously been able to see that something very profound happened. This object got so bright that it was visible to the naked eye in the nighttime for several months. I spent the year of 1987-88 in Australia because unfortunately this object was visible only from the southern hemisphere, studying this particular object among other things. Now, if they're so rare, how can we possibly understand how they work? If they only occur once per 100 years per galaxy, an astronomer doesn't live for 100 years. Well, the trick is, of course, that the universe has lots of galaxies. And so if they only occur once per 100 years per galaxy, if you observe 100 galaxies, you'll find one per year. If you observe 1,000 galaxies, you'll find 10 per year, and so on. So you just observe lots of galaxies, and they're relatively easy to find in other external galaxies. Here's a supernova that went off in 1995 that was photographed by a graduate student of mine here at UW and myself from an observatory in Chile. And you can see they're not hard to find. You'll find them only by accident. You never get any clue about what star is going to do this. If you study these supernovae, you discover that they follow a fascinating pattern as this cataclysmic explosion happens, literally destroying the star. And in particular, they suddenly just appear out of nowhere. You had no hint. And as you watch them day after day, they get brighter, 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 and so on. In fact, if you made a plot, a graph of each night watching this object, watching how does its light output evolve with time, you would find that it zooms up incredibly quickly to be extremely bright, and then over a period of about a year or so, fades back down into invisibility, the star having totally destroyed itself. But when it's up there at its brightest point, let me tell you how bright it is. It is as bright as 100 billion individual stars. Now remember, a whole galaxy of stars contains only 200 billion stars. So in fact, if you look at this picture again, you can see why at maximum there's about as much light there as there is in the whole galaxy of 200 billion stars that hosted it. So these are indeed cataclysmic events. And in this enormous explosion, more nuclear cooking goes on. Everything else in the periodic table is cooked in that instant, even if it was energetically unfavorable. I mentioned to you that it's not very useful to merge two iron nuclei together. This explosion doesn't care. Everything else is made at that point. So how are we doing in explaining how the periodic table goes? Well, in fact, now we have a mechanism, namely the cores of supernovae, to explain how everything else in the periodic table is cooked. Now, I mentioned to you that many of these elements are very, very obscure. You know, so you might say, who cares where the praseodymium in the universe was made? Or, you know, how about the yttrium? You know, I can't even pronounce it, much less spell it. But I want to point out to you that in these elements made in supernova explosions are actually some very common things that are so common on Earth, even though this is a rare event, that we use them in our everyday lives. For example, nickel, copper, tin, zinc, lead, all the caveman elements, okay, were made in an exploding supernova more than 5 billion years ago, long before the Earth was formed, and they are fairly plentiful in the galaxy. In fact, they're so plentiful that we virtually give them away. So the pennies in your pocket, the copper in this penny was made in the core of an exploding supernova some 5 billion years ago or more. There is no way that the Earth or the Sun could do that. So would you like to carry home part of the core of an exploding star? The nickel in this nickel, they don't pay professors very much, so this is going to stop pretty soon. Right? The nickel in this nickel in the periodic table, these nickel atoms were made more than 5 billion years ago in the core of an exploding star. The tin in your tuna fish can. I mean, it must be fairly cheap. We make it into tin cans. This tin was made in the core of an exploding supernova several thousand light years ago, many billions of years, several thousand light years away, many billions of years ago. No, I won't do that. That's all right. By the way, the legacy of these very complex nuclei that are made in these supernova explosions extends beyond just these common caveman metals. As you may know, some of these very complicated nuclei up here are what we call radioactive. They, for no apparent reason, spontaneously eject particles out of their nucleus. You're just standing there watching your own business, minding your own business, watching some praseodymium, and suddenly a particle pops out. So I've actually brought some along tonight to show you that that actually happens. So here is a little strontium. And the Geiger counter is recording those particles that are spontaneously shot out of the nucleus. Here is a little cobalt, ejecting particles. Here is a little thallium, a very little amount of thallium apparently. Okay, now, all right, so what? Well, you know, why are we playing Ask Mr. Wizard here? If you think about this a little bit, you realize, well, these particles ejected from the nucleus, they carry energy away with them. Where did that energy come from? Who paid the energy bill? Who said to thallium, okay, I'm going to charge up all your springs now so you have energy to toss these particles out for another several billion years or so? Those springs were charged up in the collapse of that supernova. That energy was injected to squeeze down those springs in these rare elements, and then those springs started popping up for the next few billion years, and they are still popping. So the energy that originally energized the decay of these complicated nuclei is also a heritage from this incredibly rare stellar event, the supernova. It makes sense to ask the same question that I asked about elements cooked in red giant stars. Okay, supernova cooked these very exotic complex nuclei, but how did they get to us? How did the nickel from the core of an exploded supernova get into my nickel? How did the tin get into my tuna fish can? And the answer is, again, that supernovae offer free home delivery. After the explosion, a cloud of these elements expands out to fill the interstellar medium with this newly enriched gas carrying the nickel, the cobalt, the zinc, the tin, the copper, and all those unpronounceable things like the praseodymium and the yttrium and all that, delivering it back into the gas in between the stars. This is a so-called supernova remnant that is the result of a star that exploded in our own galaxy in the year 1054 AD. And as we watch these things explode and get bigger and bigger, they're beautiful to look at. By the way, the one in the Magellanic Clouds in 1987 has evolved into a very interesting looking expanding remnant. If you look just at where the exploding star used to be now with Hubble Space Telescope, you see this rather strange-looking structure. If you zoom in with Hubble Space Telescope and look at the remains of the 1987 supernova, here is what you see. And I'd like you to sigh again, please. That was better. Thank you. Okay, now what is this? I mean, it looks like sort of nested hula hoops. I mean, how did it possibly get that way? And there's a solid astrophysical answer for that. It's just two words, and it's nobody knows. There is no way anyone would have predicted a structure like this if it hadn't been observed by Hubble Space Telescope. So these remnants are very exotic things, but what they share in common is that they expand out into the bulk of our galaxy, getting ever larger, ever and ever more diffuse. This is one that's about 1 million years old, and they continue to get bigger and bigger. They're very beautiful. These are all images taken by Hubble, until they become almost imperceptible, delivering this gas back out into the interstellar medium. When we take observations in detail of these remnants of supernova, by the way, we can see a large amount of these odd elements like zinc and copper and lead and stuff like that in these elements. So it's not speculation that this is how they get back into the galaxy. We can actually see the product rolling out the factory door. By the way, I mentioned to you that these supernovae occur almost only 1 per 100 years in a galaxy of 200 billion stars. We have not had one in our own galaxy, the Milky Way, for 400 years. So we are long overdue. It's a random probabilistic process. It is quite likely that either in your lifetime or at least your children's lifetime, the next supernova in our own galaxy will go off. There's kind of a betting pool amongst astronomers about which star will it be. You might as well guess two because nobody really knows. One of the candidates is this star that many people have been looking at called Eta Carina. When you observe this star from the ground, it's behaving in a rather odd, chaotic fashion. It's changing its brightness, and it's even changing its chemistry in some very weird, irregular way. It's clear that these people never took Astronomy 101. It's not following the normal rules. When you take a close-up image of this object with Hubble Space Telescope, what you see is this. This is your final sigh for this evening. Very good. And this looks like a painting or a drawing, but it's not. It's an image. It's a photograph taken by the Hubble Space Telescope of the center of that star, Eta Carina. So will this be the next supernova in our galaxy? I'm not sure, but it's clear that this star is in some awful kind of trouble. By the way, when the next supernova goes off in our galaxy, providing this next burst of cooking the complex nuclei, unlike many other things in science, there will be no controversy over who discovered it first. Okay? It will not be called Supernova Smith. It will not be called Supernova Jones. Unfortunately, it will not be called Supernova Margon. 3 billion people on the Earth, namely half of the Earth's population that happen to be facing in the direction of the galaxy where this thing goes off, will all look up and say, "What's that?" So this thing is going to be called the supernova, without any doubt. And it may happen in our lifetime, or it may happen later. It will probably be visible to you even in the daytime with the unaided eye for a few months, and in the nighttime for a few years. Okay, now we've seen now that red giant stars manufacture certain of these complex nuclei. supernovae manufacture other of these complex nuclei. That gas is delivered back into the gas between the stars. Let's go back to one of my two constellations, namely the Orion Nebula. What happens to that gas? Well, if you look at the Orion Nebula through binoculars, in fact, some people claim they can even see it with their naked eye. If you look down here in Orion's sword, there's kind of a little fuzzy patch. If you look at that in a telescope, this is a Hubble image, that is interstellar gas. And in fact, it is interstellar gas that is collapsing to form new generations of stars. That is, the gas here in Orion has been enriched by these sources of cooking in red giants, distributed back to the interstellar medium, cooking in supernova explosions, distributed back into the interstellar medium. And it is today, as we speak, collapsing into new generations of stars. If we use Hubble to make a blow-up of just this very tiny section of the image, we see this. And these little nodules measure in length about the size of our own solar system. These are new solar systems in formation, forming out of gas that has been enriched by these generations of supernova explosions and red giant stars. And so we find these structures actually all around the galaxy. This is one of the most famous images ever taken by Hubble. I'd love to have the t-shirt concession on this one, right? I could retire. This is another region of star formation, of gas boiling away to expose newly formed stars containing this enriched material. Well, the title of this lecture started Cosmic Recycling, and I hope you can see now why. The Big Bang occurs, cooks hydrogen, helium, and lithium, delivers it to the first generation of stars and galaxies. That gas, which we call the interstellar medium, collapses to form stars. Those stars live for a few billion years. They evolve to this retirement stage, which we call red giants. These more complex nuclei are cooked in red giants. That material goes back out into the interstellar gas, often in a quiet way, for example, in the planetary nebulae, occasionally in a violent way, in the sense of supernovae. That gas is delivered back again, and then that interstellar gas collapses to be new generations of stars. But in fact, each time it does so, it contains a little more of the more complex nuclei from the previous cooking stage. And so this truly is a cosmic cycle. Nature is terribly economical with her nuclei, and each new generations of this circle contain more and more of the hydrogen and helium and lithium that we started with, converted into heavier and heavier elements. By the way, if you feel like that you'd really like to test this somehow, this really sounds like some kind of fiction, it happens to be the case that the gas in the interstellar medium doesn't pervade our entire galaxy. It's only in certain parts of our galaxy. So there are some stars that are actually, by bad luck, located out of the gas layer. That means that if this whole concept is right, they should not be able to participate in the recycling. They should have only the early hydrogen, helium, and lithium, and almost nothing else, because they didn't sit in the recycle center and repeatedly get new generations of this gas. If we look at those stars, and you can find these stars in these structures called globular star clusters that hover up attached to the outskirts of our galaxy, out of the recycling layer, and we examine the chemical composition of the 100,000 stars here, we find there are very few complex nuclei. These stars are mostly hydrogen, helium, and lithium. They didn't participate in the recycling. They have no complex nuclei, exactly as we expect. So there's very elegant observational verification of this. So where do we stand in this story now? We were trying to make all the elements in the periodic table of the elements. We now understand that hydrogen, helium, and lithium, the first three are made in the Big Bang. We understand that the next couple dozen are made in the cores of red giant stars, and we understand that all the rest are made in supernovae explosions. It's not that complicated. There are actually only 3 different factories to manufacture all of these elements that then continue to recycle to make all of the elements in the galaxy. And so I'd like to tell you that I hope now we've kind of moved the next doll down here. And the question started, is there a smallest indivisible element? And the answer is yes, those are called atoms. The next question was, where do the atoms come from? And we've actually now moved down to the next shell. We know where all the atoms come from. And I think that you'll agree with me that it's a terribly elegant picture. The next time that somebody says to you, oh, astronomy, you know, that's nice, but it's billions of light years away and happened billions of years ago. What possible relevance could that have to our lives? Well, the second part of the title of my lecture comes into play then. Everything you breathe, everything you see, everything you eat, everything you smell, every atom in your body was manufactured in a star. We truly are made of stars. Thank you very much.